is going to be Blackboard talk, so please interrupt. Oh, is it filming or
Yeah,
Skype or
video.
video? Okay,
Yeah.
so
Yeah, it sounded right.
I'm scared because there are many
I shouldn't
political
have warned you.
correctness in this country. So. Okay, so I'm going to talk about several ideas about particle production, and especially application for the inflation and Relaxion. Recent idea for the a kind of solution of the weak scale. But it's not necessarily two of them are related. But okay. The project was started from the Relaxion, but in the end we noticed the particle production is kind of interesting phenomenon, and investigate many directions, and the hundreds failure. But I also discussed about the failure. But particle production is kind of like a very, very interesting phenomenon in general. So they present basically three ideas of particle production. One is for the Relaxion application, using applying some known phenomena of the modular trapping. So I introduced modular trapping. And also in the second, I discussed particle production mostly for the inflaton friction. And finally, I come back to the Relaxion. So I talk about the reheating, possible reheating in the Relaxion scenario. I call it relaxed inflation. So, because the Relaxion is inflaton in this case. So please feel free to ask questions. And okay, so maybe because this is relatively close to the Stanford, maybe people are familiar with Relaxion in Berkeley. I review about the Relaxion idea, including to clarify the notation and so on. So the Relaxion was proposed, of course, to solve the kind of hierarchy problem. So if I write down the standard model, so there is the potential is just this. This small h, because big H will be happy. So then we know, of course, mu square is almost weak scale. And then the question is that because this term is not, this mass scale is not protected by any symmetry, people expect, okay, this can be a higher value, but we observe this is weak scale. And why not, for example, much smaller than Planck scale or any cutoff of the theory. So this is, of course, one of the biggest motivations of DSM. And people usually tap this problem to introduce by introducing a symmetry, right? So if it's SUSY, this term is the boson and the fermion are related, and then kind of chiral symmetry protects this kind of mass term. So then the mu square is technically natural. But the recent proposal of the Relaxion mechanism is somewhat different. Relaxion is by Graham. Okay, I skipped the reference. I just skipped the archive number. Archive number is 407. Okay. So Relaxion is a relatively different approach. So not to introduce symmetry for this term, but try to reduce this a mass term. The mass term was originally at the cutoff scale, but the cosmological dynamics drives the cutoff scale down to the weak scale. So this is a Relaxion mechanism, so I write the potential. So for the Relaxion mechanism, I need to introduce the Relaxion field, which is phi. And phi has some shift symmetry. So shift symmetry, like axion. So I have this. There is some kind of symmetry, and there is the small breaking parameter. The breaking parameter. making of this symmetry. So M is some technically natural small parameter. And then the mass term is now Relaxion dependent. So the Higgs mass term is like as you can expect, like has a size of the cutoff square. But now there is big difference like this. So there is some field dependence. Or the mass term itself has some field dependence. So, and this is what Relaxion does. And the Higgs coefficient is same. And there is another term, two other terms, which is potential of the Relaxion itself to roll down. And another thing is phi of the so you can imagine like a phi for a moment, like it's like an axiom. So phi couples to the GG door, and there is some, if there is a symmetry breaking, explicit symmetry breaking, and the breaking parameter is only one, always every breaking, explicit breaking, I need an M as a square. And but there is like apart from this breaking, there is shift symmetry. For example, this has a shift symmetry. Okay, so to be more explicit, V of phi is like I want to have some dependence of the phi, yes, and then at the leading order, naively expect that like a minus lambda squared and phi. 1 power of phi, I have 1 power of n, or maybe there is higher order. And something. But basically, this is like sufficient for the sake of discussion. So the mechanism is like this. So the Relaxion potential E of phi is like this, and starting from, let's say, some large negative value, or 0 is fine, and then potential is like this. So I start from I call this is mu square. So mu square is positive. This is the initial condition. So I start from the unbroken phase, and then the size of the Higgs mass is as in the naive expectation, the size of the cutoff size. So I'm happy because like okay, actually the Higgs mass was large because it's not protected by symmetry. And this is the initial condition. Okay, so but this is during the inflation, and there is a slope of the potential like this. And the Relaxion field, this is phi. The field value is changing. So this is not important, but the phi is changing in time, right? Simply because there is a slope. And because there is an inflation, like a phi is not going down like as a free fall, but because there is a redshift, there is a Happle friction, the phi going slowly because the universe is expanding and there is a friction, and phi is changing value slowly and slowly. And then,
so in what sense does that minus lambda squared m phi term have shift symmetry?
So, yeah, this is explicit breaking of the shift symmetry.
Oh, it is.
So
okay.
this is let's say spree of the breaking. So I have the one breaking source, like I have to write down the explicit.
And then the second term you wrote down is also an explicit
right.
breaking.
So
Okay.
I have 2 power of m, 2 power of phi, and then I put the 2 power of m. Okay, so the phi, the Higgs mass is starting from the cutoff size. And then phi is changing, and as you can see, phi is like becomes larger and larger. And some point, the mu square becomes 0, right? So starting from the very large value, but because phi is scanning the value of the Higgs mass, at some point the Higgs mass is equal to 0, and above this, the electric symmetry breaking happens because mu square becomes negative, and then something more different happens. Is this like a topological term? You can imagine this is like an axion barrier. So some, let's see, this is like an axion potential. So, and this prefactor is, if it's axion, the lambda, like a barrier term, is roughly given by the n pi squared, f pi squared, right? And the n pi, the pion mass is 0 if the quark mass is 0, but quark mass is non-zero if there is a gap. So because the pion mass is proportional to the quark mass, pion mass square is proportional to the quark mass. So there is some let's say d and d and f pi third or something like this. So if the depth is 0, the quark mass is 0, so this potential does not exist. But once the electric symmetry breaking happens after here, the depth is non-zero and then barrier forms. And this kind of barrier forms after here, so like this. And then phi will stop at some point if the barrier term and the derivative of the phi equal to 0, the phi stops. So then we should identify, oh, this is the point. So let's say phi electric. So I plug this phi electric back to the Higgs mass, and this combination will be the observed weak scale. Okay, so this is the relaxion mechanism, and this is not my work. So the implications of this model. So after there are several constraints they have to consider, and then cutoff they achieve is something like 10 to the 7 GeV, depending on the decay constants. So I take the axiom that case. And this is a cutoff they can achieve for the Q3 axiom case. And the mass parameter, this small mass parameter, which is technically natural, is quite small, like 10 to the 33 GeV. So extremely small value. So this is the value they get from considering several conditions. And the other implications. Other implication is that by construction that I need a large field excursion. So because I want to scan the Higgs mass from very large value to the almost 0. But the coefficient of the phi, this small m, is very small, as you can see, like 10 to the minus 23 GeV. And the field excursion I need is this amount. So this is like a much larger than that. So this is of course a problem. And people talk about the UV completion about this. This is kind of ugly, but there is a way out. So this is one implication. Another implication is that E-fold is also super large. So E-folding is like should be larger than Hubble square divided by m square. Again, like any Hubble scale, this small m is like ridiculously small. So then the Hubble scale is again like much larger than 1. So like a huge E-folding. I remember like they talk about like 10 to the 50 E-fold or 10 to the 60 E-fold. So this is one implication, another implication. And if this phi is Q3 axiom, actually there is a strong CP problem because there is an axiom potential, but not only axiom potential, but also that there is the slope of the phi. So the axiom potential and the original slope have to be balanced. So the final value of the theta should be order 1. So there is actually non-zero theta phase at the end of the dynamic. So it doesn't work for the PCA also. This is the original proposal. And there are, maybe you can imagine, there are many aspects it's better to be improved. And it is true, and I try to improve several aspects. But the interesting thing is that Relaxion, so okay, there is an essential ingredient. Basically, there are two ingredients I need for the Relaxion. One is I need something special at the Higgs mass equal to 0. So something special at the Higgs mass equal to 0. In this case, at Higgs mass equal to 0, symmetry breaking happens, and because of symmetry breaking, the axial potential appears, and then this can stop the phi. So in this sense, it is something special. And then I try to replace this. So in the Relaxion case, the axion-like wiggle, this wiggle is taking the load. And this is one thing. And another thing is, as I said, I need some dissipative force. Also, I have like a very nice model to have this value and this value, but if the dynamics happening, for example, not during the inflation, there is no enough Happer friction, and phi just started from here, and if there is no Happer friction, just start it and then get kinetic energy, more and more kinetic energy phi gets, and then even there is a point like this, the phi has already have enough, too much kinetic energy, and the phi overshoot from the right pole. So the dynamics should happen, in this case, should happen during the inflation, because the inflation removes the kinetic energy all the time. So then phi rolls slowly. So this is another essential ingredient of this scenario. So one is something special at Higgs mass equal to 0, and the dissipative force. Okay, so why I'm talking about the particle production as a title? Because like a particle production can actually contribute either or both aspects of this. So for example, particle production could happen when the light degree of freedom appear, or particle production itself can provide a dissipative force of the inflation. So this is why I talk about the particle production. So far fine. Okay, so then I give one simple example of the particle production, so-called modular trapping, and then I try to apply this modular trapping to the Relaxion mechanism, especially for wiggle. I try to replace the wiggle. Okay, so as a toy model, so the modular trapping is not going to work. Modular trapping itself is the work that sometimes work. Here is useful. Okay, so they consider this kind of very simple scenario. So there are two fields, phi and chi, and the interaction is only this. So G squared, phi squared, chi squared. And phi is like a classical background. So phi is classical background. Classical field. And not only this, phi is like changing in time. So for some reason, I imagine that the situation that that background is changing with constant velocity of the phi dot. Okay, and then there is phi, and phi is, let's say, moving from the left. Okay, and particle production happens like under actually the time-dependent background, and this is one good example because the background is changing in time, so phi dot is constant. And the chi is like the particle I want to produce in this time. Okay, so the important thing is that the mass of the chi from this interaction is g square phi square. So apparently it's time dependent. It's like a relaxant. So Higgs mass has like a phi dependence and it's changing in time. And this case is also something similar because like a mass of the chi is phi square, coming from the phi square. Okay, and then the particle production happens. So I have to write the equation motion. So equation of motion of the k mode of the chi k mode is like I just use this interaction for the equation motion and the Fourier expansion. And then the equation motion of the k mode of chi is this, and
So phi is just move. Is this? Are you imagining that there's in addition a constant slope for phi, or
No,
phi
sorry,
is just
sorry.
moving because
So
you're choosing that state, or what?
For this discussion, I assume completely zero.
Okay, so it's just an initial condition that phi is moving.
Yeah. So I switch on the potential of the phi later on, but for this, it's like completely flat for the pure phi direction, and there's only this term as a
Right,
junction.
thank you.
Okay, so then the equation motion is like this, and then master, and then because I did a Fourier transformation, there is a k square, and this is like a frequency depending on the k mode, and then particle production happens when the change of the frequency of this mode. Change of the frequency is too rapid compared to the typical time scale, which is actually frequency. If the change is rapid, particle production happens. And the condition is given by this. This is called a non-adiabatic condition. So omega sub k dot divided by omega sub k squared. If this is larger than 1, the particle production happens. Okay, so to be more explicit, this is like g phi dot divided by the k squared plus g squared phi squared minus u phi. If this is larger than 1, the particle production happens. And from here I can see something. So one is that if the change of the background is very rapid, meaning that phi dot is very large, and phi dot is here. And if this is very large, more particle production happens. And another thing is that the dependence of the k is here. So since k is in the denominator, there is like a lower k mode is preferred. So if the k is very large, the particle production happens. Like higher frequency is not produced. Okay, so this is a condition of the particle production. Particle production happens if this condition is applied. Okay, and as you can see from here, apparently this is a master, like the master. And this is also master. And actually, the particle production happens around that the mass is very close to 0. around here, this condition is satisfied, and then particle production is actually happens. So the particle production happens not here and not here, but here, meaning that there is something, it is something special. Like Lagrangian doesn't tell anything, right? So no point is special. But actually, if you calculate the dynamics, actually here is something special, and then production happens. Okay, so then I can actually calculate the production explicitly.
So, I mean,
Yes.
I mean, of course, in the Lagrangian you've written, it's happening at phi equals 0, which is a special place.
Right.
So if you wanted to say that it wasn't, you might want to add a mass term for chi squared, right? I guess that's what you're imagining, right? And then it would be shifted, the value of phi. It's not, let's see, but then, okay, just go ahead. I'll ask later.
So maybe, okay, it's better to stick with this simple example. So the production rate can be calculated explicitly. The mole density of the particle is just given by pi k squared divided by g phi dot. So from here, it already tells that actually it's exponentially suppressed by k squared. So the low k mode is more produced. And so this is just mole density. So I want to know the number density, which is given by E3k and k. So this is number density, dimension 3, and this is g phi dot and 2 half and 2 pi. Okay, so this means like if the background change is very rapid, the particle production happens more, right? Because this is proportional to phi. Also, G dependence is also clear. Like if the coupling is strong, you have more chance to produce particles. So this is the particle, like a total particle production of the chi. So far, like just I talk about the particle production of the chi. But the important thing is that what is a back reaction to the phi? So so if I look at this Lagrangian naively, look at the equation motion, and then there is a constant velocity of the phi dot, and the naive expectation is like a phi just pass and then go forever. But actually, this non-perturbative dynamics tells something different, because some particle production happens, and there is some finite number density of the chi, and then the effective potential appears. It's actually there is energy density of the chi because there is finite number density, and the energy density is given by the mass times number density. It's clear. So this is an effective potential to the phi, because particle production happens here, and then once phi passed here, the number density is conserved, and this number is conserved, but the mass is changing like this. So actually this is a potential for phi, right? So once I produce non-zero n chi, the mass of the chi is changing in time because the mass is this, and then phi wants to come back because otherwise phi loses more and more energy, and then this is exactly the attractive potential.
So these chi's are non-relativistic?
chi is non-relativistic because like the lower k mode is closed.
Yeah, but it's also true that the mass is going to zero, so it's not, but you can check, right? You can compute the expected value of the velocity or something.
Right, right.
Because the mass is going to zero also, right?
Around this region.
Yeah.
Yeah, but okay.
But
So
the k
this
expression is set by, I guess, is set by the derivative of phi, so it depends on the size of the derivative of phi.
I should say this expression is only valid like a far enough away from this point.
Yeah.
If it's close, like as you said, like mass is zero, so I should have a different expression. But if phi is away from here, this is valid expression. So then this is a feedback, like the back reaction for the phi. So then there is now like a linear potential for phi. And then phi actually now like it doesn't travel as a field, but phi wants to come back because the potential is here. So then phi some point comes back, and then when phi crosses here, second particle production happens, which is actually proportional to the already existing particle because of the bosonic enhancement. So I already produced particle, and since particle is already there, that there are more chance to produce particle, and this is exponential effect.
Right, I would have thought that this energy is proportional to phi dot. So I would have thought that it would be like a friction term, and then once it stops, it would just stop. That's not correct?
It's proportional to the phi dot, so what do you mean?
The particle production rate is proportional to phi dot.
Here.
Yeah, so it goes to zero when phi dot goes to zero, so it looks to me like this is more like a friction force than a potential. So I'm wondering why doesn't it stop when phi dot goes to zero?
If phi dot becomes zero, the next particle production doesn't happen. So what do you mean that?
Because I thought you were telling me that it's going to slosh around because
Right.
there's an effective potential.
Right.
And to me, it looks more like a friction force than an effective potential. It looks like it would stop the first time it would just stay stopped the first time it stops.
So you said the number density is conserved.
Number density is conserved after like this region. This region like the number density is really not conserved. After here, like number density is conserved.
So this potential is after you get out of that region?
Right. So this potential is only true like far enough away from this point.
So what's causing that? So what's causing that potential is not particle production. Because
Okay. So because particle production happened, and this produced particle
their back reaction.
back reacts.
Oh, I
Yeah.
see.
So
But then there's also a radiative question, right? I mean, given the potential you've written,
Mhm.
there's no symmetry that stops a mass proportional to phi squared. Of course it will, right, a phi squared mass term. Of course it will be suppressed for small g, but so is this particle production. So since the radiative generation of a potential, I would guess, beats this.
Okay.
Right.
I understand. So here, like I completely ignore that radiative correction, and actually this scenario I tried to apply for the Relaxion bump, because that is try to replace it. In the end, it doesn't work. So actually, before including the radiative correction, actually, so but I just wanted to give an idea. So that in this case, there is something. In this particular case, there is something special, which is Bose enhancement. So it's just interesting to note, but I'm not really using this Bose enhancement. So okay. So particle production. So in this case, so the time and phi. So naive expectation is that phi is rolling from negative to the minus infinity to the plus infinity, like this. But because of the back reaction, phi comes back, and then particle production happens in the second time, and the second time has larger particle production and more attractive force, and then so that this is a point that the mass of the chi equal to 0. So massless particle is favored in this dynamics. This is a message I wanted to tell in this simplest example. And something really special, it is something special at some particles mass equal to 0. So naively, okay, so Higgs mass, I want to, like, it's something small compared to some other scale, Planck scale, and then I want to use this mechanism for the Higgs times.
So,
Yeah.
Every time, okay, so every time you cross,
Yeah.
you make more of these
Right.
chi fields.
Right.
And so there's a bigger, the potential is forcing you to the origin is getting
Exactly.
more, but the friction is still enough to overcome that, so that's why you settle down the way you're settling down. That's
Right.
what you're saying. Okay, I understand.
Yeah. So this point, that's fine.
Okay.
So this is so-called modular trapping phenomena. And then, okay, I give very simple exercise for the application of this mechanism. So in the case of relaxion, unlike this example, there is potential of the phi, right? So this is non-zero because like I want to like a phi wants to go. So there is like some potential, and I want to parameterize like this was a previous example, and that n can be written by like g phi. So g is also like a breaking parameter, but a dimensionless version of the breaking parameter. So I sometimes use g instead of n, and this is because I'm already using g. It's more straightforward to use. So this is the original potential of the relaxant by just after the spurial analysis. And okay, so the question is that let's say there is some massless particle appears correlated to the Higgs wave, and then the question is that how much particle I can create, how much of particle I can create, and then depending on the size, I can maybe stop at here if the bump is large enough. Okay, so the calculation is very simple because the formula is already here. So I won't use this formula. So what is the size of the n prime? And there is only one parameter. I don't know in this expression which is actually phi dot, and the phi dot can be at most a cutoff square, and you can imagine that if I start from like a random place about here, and then if I move from here to here, typically the potential energy is like the phi lambda to the force. Then the kinetic energy I get from here to here is lambda squared. So the phi dot is at most or order of the lambda squared. And if this is during the inflation, of course, this is much less. But I try the best case scenario, and this sense of phi dot is smaller than lambda squared, and just plug in. So I just put here g lambda squared. And this. Okay. And then dynamical potential, so let's say effective potential is again like n chi. So n chi is now g phi, and this one is g ignoring 2 pi stuff, I just count how much power of the G and lambda. So G is like a 5 to the second, 5 halves, and lambda by dimension is 3, and there's 1 power of 5. So since G is small parameter, if G has like a higher power of G appears in effective potential, like we always do, the original slope is much steeper compared to the effective potential. So this scenario was attractive because like the particle production favors the massless particle, but the generating potential is too small compared to this potential. So this doesn't work for the relaxing mechanism as a bump. Is it okay? Is it clear?
Yeah, I would guess that this is I think what makes the original, GG dual axion coupling special is that it preserves discrete shift invariance. And so no matter how big that term is, it will not change the slope of it will not renormalize the slope of the potential. And that's somehow what I think is special about that term. But this term right here, the couplings that you're adding, they break the shift symmetry completely. And so then it seems intuitive, it's intuitive that they would be, the effect on the slope would be smaller than the UV divergent contribution, which is, after all, the minimum number of breaking terms multiplied by the biggest possible scale.
I see what I'm saying. Yeah.
So I'm just saying intuitively, I'm not trying to, I'm just saying intuitively this makes a lot of sense.
Okay.
You need something that treats the shift symmetry in a more clever way
I see.
to get the thing to
So in
stop.
the original model, in this sense, like the barrier terms, phi dependence in the cosine. So there is a discrete symmetry in there.
Yeah, so it's the fact that, because you can't make this, it's the fact that it's really the cosine thing is a different effect than just affecting the slope. Here you're trying to affect the slope, so you're competing against, you're broken of the same symmetries as the original slope, so anyway, it doesn't...
Right. Doesn't work.
You see what I'm saying?
Yeah, but so there are 2 more comments, so it doesn't work already, but even if I have produced like a number density high enough comparable to this, by some reason, still this mechanism, this approach doesn't work, because one reason is because I try to balance this potential and dynamical potential, and this potential doesn't change due to the redshift, but the dynamical potential is coming from the number density. So number density get redshifted, so this size becomes smaller and smaller. So meaning that even in the beginning that I reproduce a light weak scale, since one of the potential is changing in time, the weak scale is changing in time, which is very bad for many reasons. For example, BBN. Another thing is that even if I achieve the larger size of the n chi, the size I need is like n chi is order of the lambda to the third, which is huge number. And what kind of number density can do this work? And nothing, because what is the particles in the current universe, like a neutrino or dark matter, for example, but the size is like order, the energy density is like 10 to the minus 3 to the fourth, like dark matter or something. So this is way smaller than the mass scale I'm considering. So by also this reason, this approach doesn't really work. Okay. Maybe how much time actually?
Have any of these approaches
15 minutes.
solved?
10 minutes?
15.
Sorry.
Have any of these approaches yet potentially have solved the large number of defolding difficulty?
So this is related to what I'm going to talk. So Yeah, actually it's related. So if I can replace the wiggle, like originally there was wiggle, and then the potential is coming from like a number PCB side of A, and then if I can replace this wiggle with some other stuff, like the constraints, like for example this from here, this is a dynamical potential, and I have this potential. This is a potential, and I want to make the derivative equal to 0, roughly speaking. And then lambda, let's see, PCB, the force or F should be comparable to the n lambda square, right? So since this size is so small, m has to be very small if I want to raise a cutoff lambda, right? So this is a part of the reason why m should be small. And the e-folding is roughly the h squared m squared, right? So then if I can remove this condition by somehow, I may be able to avoid the large e-folding. So this is related, yes. But not in this case. Okay. So I'm surprisingly running out of time. Okay, so maybe I give up the third idea, but I'll try to explain the second idea, which is not necessarily about relaxation, but using this modular dropping and try to use modular dropping or particle production as a new dissipative force of the inflation. So the usually inflation happens because the equation of motion of the inflaton is like this, and then we have to prepare very shallow potential of the phi. So this is very small, and then usual solo condition is that phi double dot should be smaller than 3h phi dot, and then equality is 3h phi dot plus e prime roughly 0. Okay, so this is a usual solo condition, but there is a kind of alternative scenario for the trapped inflation. Not only this scenario, but the trapped inflation. And some of the authors overlap with modular dropping, and you can imagine they will use the trapping mechanism by name. So what they do is a bit crazy and radical. So they have this kind of interaction. They introduce many chi's in this way. So now I have chi sub j, because I have many chi, and phi is again like some classical background. In this case, phi is in inflaton, and I have like so many to the many particles of the chi. Okay, so this is the starting point of their case, and then the cartoon is like I have phi 2 and phi is going. D of phi is non-zero. Okay. Can be anything. But there is so many particles which can be masses in the different places. For example, here, like a chi naught equal to 0, and here, and chi 1 equal to 0, and here, and chi 2 equal to 0. There are so many points they introduce, and they need many And then, okay, so they know how to calculate the particle production for each time. So phi is going down. Okay, so phi. So for simplification, like they consider the equal spacing. Between phi j plus 1 minus between phi j plus 1 and phi j is the equal distance delta, and then each delta find the particle or the massless particle, but different particle, right? So here and here and here and here, and particle production happens, and potential is generated, potential is generated here, potential is generated here, and so on and so on. So, why they are doing this? Because that they want to get the friction from this potential rather than happen. So the equation motion is because I already got here. Equation motion is modified because now there is this kind of potential. And then slow roll happens not because of the upward friction, but the dynamical potential. So phi double dot should be smaller than 3h phi dot. This is the same as before. But 3h phi dot should be smaller than b prime of phi. And then b prime of phi and b pi is 0. So this is a new slow roll condition. And then slow roll happens not because of the aperture. And to realize that, of course, they have to introduce many particles, and I just want to give the result. What is the size of the dynamical potential, especially b prime? So b prime, b sub chi prime can be calculated g and 3 pi and so pi dot so this is the b sub chi prime condition. And one interesting thing is that the slow roll condition for the phi dot is totally different from the conventional inflation. Phi dot, usual slow roll inflation is that phi dot is given by 3h, something like this. This is the usual. But now trapped inflation case, the phi dot is given by this equation. The phi dot is completely different structure. So, for example, the potential dependence has a different power, and the H dependence is also very different, like H in the numerator or the denominator. And then this kind of difference gives like a lot of difference in the power spectrum and so on. And I just say several.
Can I just ask, is it correct that this v chi looks like a mass term for phi centered at phi sub I? Is that basically right?
Right.
So this condition that you boxed there is kind of it's sort of tuning these guys so that those mass terms. So I guess what I don't understand is that it seems like if they're mass terms, they keep growing as I go away from the respective minima. So it's not clear to me that this results in slow roll.
I forgot to say something
Yeah.
So this B chi is basically coming from this term, and this is like as I wrote before, the sum
Oh,
of
it's
the
linear, I'm sorry, it's a linear coupling.
right linear. But actually, for example, if phi is here, of course I produced a particle here, but this particle is not, the number density is not relevant because of the redshift. So I have the chi j, but I have tj. So for example, if phi is here and then I produce particle of the, let's say, chi naught, and then there is an attractive potential, and then take the derivative, so the linear power of phi is removed. And then phi is around here, I produce the next particle, and if the number density is conserved, there is a constant attraction force for the phi from here. But because this is during the inflation, so this number density gets redshifted, so becomes smaller and smaller.
Yeah, but I guess I would have thought that if you're in the regime where Hubble friction, like let's say you didn't have any of these chi's, you're presumably interested in the regime where the Hubble friction is very small, so you would have, right?
Yeah.
So you'd have much, you would maybe, I'm confused about why you're even requiring phi double dot.
Oh,
It's already, you're requiring the slow roll condition even though you're not being slowed down by Hubble friction, but you're...
okay. Why do I require this?
Why don't you go ahead and finish? I think I'm confused about so many things that I'm just going to stop you, so
No, it's
just
okay.
go ahead and
Yeah.
I'll ask,
So,
I'll talk to you later.
Okay, so this is their scenario, and then so there
Just
is
to clarify one thing,
Yes.
the second equation for phi dot is
Yes.
the one that's appropriate when you have this nu v chi acting.
sorry this equation.
Yeah, that comes from the nu v chi.
Right. So from here, so I have the phi dot dependence here,
Right.
and then B prime here. So then this power is correct because of this,
Right.
and then I just move everything else to the phi prime, and then I'm sorry, G has also.
Other. Yeah. Okay.
So G and phi dot has a power of the 5 halves, and then I move the 2 pi cube and delta H to here, and then make the two fifths.
Oh, I see. Okay. Got it.
Is it
right?
Yeah. So that's why like I have a different dependence on the B prime or H compared to the conventional
Right.
slow case. And actually the one simple extension of this scenario, this is trapped inflation scenario, gives completely different phenomena. Very, very interesting for me actually, which is introduced. So let's say I have a name, Kohsaku slow mode. So this new phenomena happens once I include decay term, meaning that now, so here like each chi j is completely like independent of the like chi interaction doesn't exist here, but I introduce some interaction I j squared and I l such as this L. So which means that there is interaction. So if one of them is heavier, using this interaction, chi can decay to the other. And then borrow this phenomena, borrow this scenario, and add this decay term, and very interesting thing happens. Because, so, phi is rolling, and then it's like that. different particle becomes masses. And here is like a chi naught becomes masses. And as before, the particle production happens. Chi naught is produced, right? And the chi naught is produced because the mass of the chi is 0, or nearly 0. So this is a point that I can produce, chi naught, right? So then, the interesting thing is that if phi arrives here, where the chi 1 is massless, is actually chi naught mass is g delta, because phi is changing in time. So the chi naught is massless here, but here chi naught is not massless anymore. It's of course massive particle because the mass is changing depending on the position of the phi. So this guy is heavier than this, and then I produced a particle here already. So this is I can see. And actually, I don't need the particle production here anymore to accumulate the number density because the chi decay. So now chi naught is heavier. So chi naught have a number density of m naught and can decay to the chi 1.
So the decay can compensate the redshift dilution?
Exactly. So this is very interesting. So this is very important point. So this is an exponential effect because, and then move from here to here. So chi 2 is 0, massless. And then, okay, so all the chi 0 number density transfer to the chi 1. So let's say chi n1 is roughly 2 times n naught. And then once the phi arrives here, the chi 2 is massless, but the chi 1 is massive, g delta. So the chi 1 can decay to chi 2 and chi 2, and because I have two particles, I have one more branch. So the number density of the 2 here is roughly 2 to the 2 and 1. Okay? So after n points, I have 2 to the n and 1. And since I'm considering this is during the inflation, like the velocity is roughly constant. Okay, so the number of the n, big N, can be replaced by the phi dot t divided by delta. So like the phi dot t is the amount of the field phi travels for the time t at the time t divided by the average distance delta. So this is n. So then it's very interesting because effective potential is 2 to the n, and the n naught is coming from here, and actually this is not so important. And then some master and chi n, n minus chi n. And then redshift. Okay, so and then usually redshift, like we move this kind of number density away, but since this phenomena is exponential, it's actually comparable to the redshift. So if I do some mass, the effect is like the G and naught, the I minus I n, and the exponential minus CHT. This is coming from the inflation, or the redshift of the inflation, plus log 2 of the phi dot. So this is a big N. So as you can see, the phi dot is roughly constant during the inflation, and delta is a parameter of the Lagrangian, and rho 2, of course, is just coefficient. And the time dependence in the exponent is same. So it like depending on the phi dot, that actually these phenomena can compete with even the redshift of the inflation. So and if so the condition of the throw I'm interested in is this again, but the phi dot condition is completely different. For example, this H delta 3 divided 2 plus H2. So as you can see, that the phi dot has completely different structure. For example, logarithmic dependence of the potential. The conventional solar inflation, like the very shallow potential is crucial because the phi dot is given by directly B prime. And now, like this radical effect can be computed with redshift. And then the dependence of the B prime, the slope of the potential is only logarithmic like this way. So, and then the phi dot is given completely different, even from here. So this is a model without decay term, but just adding the decay term, like moving one regime to the completely different regime. I found this is very interesting.
So did this solve the E-folding problem?
Not sure because I have to calculate. So they, like trapped inflation, they calculated the power spectrum and so on to consider to have a relevant constraint. And this is actually non-trivial calculation. And then they achieved the E-folding. For example, field excursion is ordered n plan. The E-folding is like requiring E-folding is 50 or 60. So it's not crazy number like the excursion is. And as you can imagine, like a decay term is basically, I think, is improving this scenario because it's enhancing the effect. So I hope that, like for example, field excursion becomes shorter than even n Planck. But this requires I need to calculate the power spectrum and so on. This I haven't done. Okay, so this is something different from the Relaxion thing. But if I want to like embed this kind of scenario in the Relaxion, maybe I don't want to use too many scalars because I wanted to solve the hierarchy problem, but I have too many scalars. But I think this mechanism works equally well if I replace this chi with fermions. So fermion particle production is roughly similar. And since I'm not using the boson, since both scenarios are not using bosonic enhancement, fermions I think works equally well. But it's not entirely clear like how can like combine this scenario with the Relaxion. So I should say this is a bit different phenomena of the particle production. Okay, so maybe I'm running out of time. So here is the end of my talk. Thank you very much.